Now, sometimes it is very important to find the bandwidth product of the bandwidth and gain. But before that, before finding the product, we first to study the variation of the current gain with frequency. We know that in case of common emitter configuration, the current gain at the low frequency is HFE. Okay, this is HFE is at the low frequencies. So when the HFE become a function of frequency, when the F is a high value at higher frequencies, it becomes a function. And to draw the equivalent H equivalent circuit, especially at the high frequencies, the capacitive reactances are taken into consideration. Like this is a common emitter circuit. Emitter terminal is common, emitter, base and collector. Input is given to the base input signal and output is taken at the collector side. So this is HIE, input impedance, VBE, base emitter voltage. This is the capacitance which appears between base and emitter. Okay, and this is the capacitance which appears between base and the collector. Then we have a current source, GM into VBE, and then here there is a load resistance, RL. Here is the output. Now in order to find the HFE as a function of frequency, output is shorted. Then to make output shorted, we can find the HFE. So how the output is shorted? That we are replacing RL by a short circuit like this. They are directly connected, the two terminals. Here it is shorted, means RL becomes 0. Now if RL becomes 0, the circuit modifies to HIE, one capacitor, CBE, another capacitor, CBC, base collector, IC and IB. Now here you notice CBE and CBC are in parallel. In parallel, the capacitance they add up. And let me say the capacitance of this is, capacitive reactance is XC, the combination. So it is 1 over j omega and the sum of the capacitance of the two capacitors. Now XC and HIE are in parallel. Now we make the parallel combination and just solving that relation, rearranging the terms. Now we find input voltage is input current into the input resistance. So we are having the input resistance, input voltage is VAB, input current is IB, and the above which we already calculated above this relation. So again simplifying, and we find the value of IB now. Now again, the current generator having current value IC equals to GM into VB, this one. This is IC, GM into VBE. So what is the definition of HFE? Output current over the input current, IC or IB when output shorted. Substituting the two values, so this is VBE actually, not VAB. So VBE cancels out denominator and numerator. At low frequency, you know what happened? This term is neglected, as the omega is very, 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 very less. And then HFE is called HFEO. GM into HIE is called HFEO. O mean for the low frequencies. So now again replacing GM HIE with HFEO, then HFE, which is a function of frequency, becomes omega is 2 pi f by definition. Now we are defining short circuit limit frequency. We are defining a new frequency, or CE cutoff frequency is defined as F beta. This is C, common emitter cutoff frequency. Let it is defined like this, and substituting this value in the expression here. So F beta, now we are introducing F beta in here in this term. So HFE becomes, which is a function of frequency, it becomes HFEO divided by 1 plus J f upon f beta. So this relation tells you with increasing f, HFE comes down. So a graph is plotted between f upon f beta versus HFE. Along x-axis, f upon f beta, which is just a number. And HFE in decibel. So straight line, then decreasing, decreasing, decreasing. So here it is decreasing. The HFE is decreasing with frequency. So if we produce it like this, and this is the asymptote. The asymptote and this point is very important. This is f beta. Here it is 1, mean f equals to f beta. F upon f beta equals to 1, mean the frequency is equals to f beta. Here it is, the decay is minus 20 decibel per decade. Decade means a frequencies of multiple of 10. So for 1 decade, the HFE comes down by 20 decibel. There is a gain when frequency is more than f beta, but it is becoming less and less. So this is very important relation. Now if f is greater than f beta, one may be neglected. So this graph shows, this relation shows just a straight line. So f equals to f beta here gives HFE equals to HFEO. So this value HFE is actually HFEO. This is asymptote. The very important topic is the gain bandwidth product. We know that the forward current ratio of the common emitter is given by this expression. And if the f upon f beta is greater than 1, then 1 may be neglected from here. And HFE becomes HFEO, mean at the very low frequencies the forward current ratio. So if f beta, at the value of the f beta is, this is, already we calculated, just watch my previous video. Now if we plot a graph between f upon f beta versus HFE in decibel, then like this is the asymptote, this is the actual curve. Actual curve is like this, and the asymptotes, asymptote, it meet at this point. This is f beta. Here the forward current ratio in decibel, this 25 in decibel, Here it is 0, and here f, it is called this frequency as ft. It's a 0 decibel. So HF, when HF is equals to 1, then in decibel it becomes 0. So if HF equals to 1, then F is called as Ft. We consider this expression HFE equals to HFEO F beta upon F. If this is 1, this F is termed as Ft. Then Ft becomes HFEO into F beta. F beta already written above. Substituting here, then Ft becomes now Gm is mutual conductance, and it is the ratio of HFE upon HIE. Now we put this letter 0 both sides. HFEO becomes GMO into HIE, substituting above. HIE will cancels out. So this is the expression of Ft. So it is constant again. So again, if we draw the graph, this is constant gain, decreases, this is asymptote, this is F upon F beta, equals to 1 here, HFE in decibel. This is here 0 in decibel. Here FD. This actual curve. So this is the bandwidth. So lower side, when F is low, the gain is constant. And when the F equals to 0, from 0 frequency it is constant. So this is the lower limit, 0 frequency, upper limit is F beta, bandwidth becomes F beta. For current gain, gain versus frequency graph, and HFEOA mean forward current ratio for the lower frequencies, and it is constant. So it shows that the product forward current ratio multiplied by the bandwidth forward current ratio at the low frequencies multiplied by the bandwidth, this product remains constant for a given transistor. So gain bandwidth, gain mean current gain. Current gain into bandwidth is equals to constant. The current gain equals to constant over the bandwidth. If the current gain decreases for a transistor, then the bandwidth of that transistor will increase.